Today I discuss about basis for a topology. Basis plays important role in topology and basis generates some element comes from topology and this topology generated by this basis. Now start definition. If X be a set, a basis for topology on X is a collection script beta of subset of X called basis element such that X belongs to tau, then at least one B belongs to script beta. That means one basis element B belongs to script beta such that X belongs to B, and let X belongs to beta 1 intersection beta 2, where beta 1 and beta 2 belongs to script beta. That means this collection. Then there exists a beta 3 belongs to script beta such that X belongs to beta 3 subset of beta 1 intersection beta 2. Then beta satisfies these two conditions and we call this collection script beta is called a basis for a topology on X. Now topology tau generated by script beta. Now topology tau generated by script beta as follows. If a subset U of X is said to be open in X, if for each X belongs to U, there is a basis element B belongs to script B such that X belongs to B and this B subset of U. Note that each basis element is itself an element comes from this topology. That means basis element are the elements of the topology. Now it comes to an example of a basis element or of a basis of a topology. We start beta collection of all circular regions. Collection of all circular region. In plane. Then beta satisfies both conditions of basis. Then beta satisfies both two conditions of a basis. So beta be a basis for a topology. Then topology generated by beta, a subset U of a plane is open if every X in U lies in some circular region contained in U. We draw some figure, some circular region B1 and some circular region B2. We draw in a plane and one point X belongs to this B1 and also belongs to this B2. That means X belongs to B1 intersection B2. Then we find a B3. Then we find there exists a B3 belongs to script B. This one obviously a circular region. This B3 obviously a circular region. and this contain this x. Then we see from this figure that second property hold, and obviously we draw a point x, then obviously one circular region contains this x. So two properties of a basis hold, then beta collection of all circular regions in plane satisfies two conditions for a basis, then beta be a basis for a topology. That means first example we done in this way. Next we construct second example. Second example is also important. Here we take this collections beta dash be the collection of all rectangular region. Same thing happen, collection of all rectangular region. Unplanned. Then these two conditions satisfy, beta dash also satisfy two conditions, also two condition for basis satisfies. So beta dash be a basis. So how we generate it? I draw a figure. Here is some point x, here some point x, then once rectangular region beta 1 contain this x, and even another rectangular region beta 2 contain this. Then obviously one rectangular region from, obviously we draw another one beta 3. Same thing for circular region. Then this one hold, if one point here, then one rectangular region beta obviously we find, and here also x belongs to beta 1 beta intersection beta 2. This implies that x belongs to beta. There exists one beta 3 belongs to script beta, such that x belongs to b3 subset of b1 intersection b2. So b3 satisfies all this, the beta script beta dash satisfies all these two properties of a basis. So script beta dash be a basis, script beta dash be a collection of all rectangular region in plane, they form a basis. Now start another example which is also more important to us, and we now discuss about it. Which example we start? We start a familiar example. We start a very good topology, discrete topology. We start discrete topology. We start with discrete topology. Discrete topology. Then we find the basis element. Basis element, how we construct? I construct if x equal to 1, 2. Then this tau topology, discrete topology, tau equal to phi x singleton 1 singleton 2. Here basis element are very good, just singleton 1 singleton 2, because singleton 1 and singleton 2, these two generate every elements. Singleton 1 singleton 2 here some problem, not singleton 1 is not singleton 2, phi and x also contain here, because if we count phi, then phi obviously belongs to this basis, and if counts x, then x obviously belongs to this basis, and if 1, then also this one belongs to, and also this 2 belongs. That means if Then collection of all one point subset of X is a basis for the discrete topology on X. Not I do something. If we take phi and x, then not a problem. But here obviously singleton 1 and singleton 2 also generate basis, because if x contain 1 2, then any point 1 belongs to x, then 1 belongs to this one. If 2 belongs to x, then 2 belongs to this one. That means just elements from set of elements belongs to this set, and these elements are belongs to some basis element. Okay, not element of topology. Element of, if element of topology we construct, then this one is happen. But here at if we take phi and x, not a problem at all. This one also satisfies this basis. But if we smallest basis, then we just want to, that means all one point subset of x from a basis for this discrete topology on x equal to 1 2, just two element set. Now we discuss x is any set. If we discuss x is any set, then we also find a topology on x. This one is discrete topology, contain all subsets of x. So contain a topology which one contain all subsets of x. Then we form a basis element. For basis element, just singleton elements. That means just if we construct here a1 a2, just singleton one from a basis element for this discrete topology. Now comes to a point. Next we discuss about some lemma. Next we discuss about some lemma which is more important for us. This lemmas also belongs to this basis for a topology. But after all, after going to lemma, first we discuss some more example. More example means we construct a topology which one phi x 1. Okay, here x equal to 1 2. This topology we find a basis. Basis equal to same thing, singleton 1 singleton 2. Okay, because we find any x belongs to x, then this x belongs to some basis element, this one, or x belongs to this one. Okay, if we construct another topology, then remaining we find a basis element upon this set, or constant according to this topology. That means we construct a set x where topology is the, which topology we construct? We construct a topology u subset of x where x minus u is finite, is either finite or all of x. That means finite complement topology or cofinite topology. Here we find basis element. Which one is the basis element? Basis element is the those elements which contains all elements of x, So which elements contain all elements of x? here x must be here x must be tau must be infinite subset of x. That means x must be infinite. So here basis elements are all singleton ones. All singletons ones. All singletons ones. All singletons all elements of x. That means a such that a belongs to x. Okay, if x is infinite, because this one is finite complement topology and this topology contain infinite subset of x, so this basis contains all singleton elements. Okay, and we generate a such that a belongs to x. Okay, all of a such that a belongs to x. So here we discuss now some lemma which are important for a basis. That means which represent some criteria of a basis which is applicable now. Now we construct a lemma. First we write statement of a lemma. Statement is so simple. Statement x be a set, let x be a set, let script b be a basis for topology tau on x. Let script b be a basis for a topology tau on x. Then tau equals to the collection of all unions of elements of script beta. Then tau equals to some union of element of script beta. That means some beta x, some beta belongs to script beta. In this way we represent some topology. That means some union of some basis element represents some topology. Union of some basis element represent this topology. Now we start proof. A collection of elements beta, they are also belongs to tau. We know that a collection of elements of beta obviously belongs to tau. As tau be a topology, then their union belongs to tau. Then their union belongs to tau. So union of collection of elements of script B obviously belongs to tau. That means union of beta, where beta belongs to script beta, is subset of tau. Okay. Now conversely we represent u belongs to tau. That means some open set belongs to tau. Then for each x belongs to u an element B, an element B belongs to script B such that x element beta x belongs to script B such that x belongs to beta x, subset of U, then obviously U equal to union of all beta x where x belongs to U. So U is the union of elements of beta. So U is the union of elements of beta and U belongs to tau implies U equal to union of elements of script beta. That means tau subset of union of beta belongs to script beta. So from this one and from this one we write these things: tau equal to union of script beta union of beta B belongs to script B. So we prove this lemma. Let x be a set and beta be a basis for topology tau on x. Then tau represent union of this basis element.